Okay, we're back to do some physics problem solving. We're working on energy this week, and I want to do an example of a problem where you might normally use kinematics or forces to solve the problem. You have to think about those things certainly in order to solve the problem, but I want to solve it using energy. Now, I grew up in the country, and in the country during the summertime, we go through a series of hayings where we grow hay and then we mow it down 2 or 3 times each summer. And after we mow it down, we bale it up. And the baler leaves those bales of hay out on the field, and then you have to drive along with a tractor or a truck, and you have to pick up that bale of hay. You lift it up, you whack it with your knee to give it some lift, some speed going upward. It goes up onto the trailer, and typically you have partners up there who then grab that bale and lift it again to throw it up onto the stack. So that process of lifting the bale and whacking it with your knee and giving it some upward speed is called bucking. So let's talk about bucking some bales. So suppose you buck a 30-kilogram bale of hay. It gets lifted 2 meters vertically while you're lifting it onto the stack, and you apply a force of 320 newtons. And what we want to know is, what is the speed of the bale at the moment that you release it, at the moment that it comes off your knee? Okay, now this is a problem that has forces that are certainly involved, and so we need to think about the forces if we're going to think about how to do this problem with energy. So let's go ahead and draw our free body diagram before we start. So we're talking about a bale of hay. That's our object of interest today, and there's 2 forces acting on it. There is the weight of the earth pulling down on the bale. That is equal to the mass of the bale times the acceleration due to gravity. We're told the mass of the bale is 30 kilograms, and the acceleration due to gravity is 9.8 meters per second per second. So the weight is, I have to punch it out here, 30 kilograms, 9.8. So the weight is 294 newtons. Okay. The other force in the problem is the force of me pushing upward on the bale, or you if you're bucking the bale. So this is the force of you on the bale, and we're told that that force is 320 newtons. Okay, so right away you can see that what we expect to happen should happen. There is more upward force than there is downward force, so indeed the bale should accelerate upward as a consequence of the bucking. Now, how are we going to use energy to get at what we want to know? What we want to know is, what is the final speed of the bale? Well, the way we're going to do it is, first we're going to compute the work done by each force. And then we're going to remember that the total work done on a system, in this case the bale, is equal to the change in the kinetic energy of that system. And then from the kinetic energy, we'll find the speed v that we're asked to find. Okay, so that's the procedure. So let's go ahead and compute the work done by each of these forces. So you'll remember that generically, work is defined to be the force, the magnitude of the force, times the distance over which that force acts, times the cosine of the angle between the force and the displacement of the system of interest. So let's look at this for each of the 2 forces. So for the force of U pushing upward on the bale, the displacement d is also upward. So in this case, the angle theta is 0 degrees. Okay? So if I use that information together with the numbers from the problem, I see that the work that you do on the bale when you buck the bale is equal to the force that you apply, which is 320 newtons times the distance over which it is applied, which is 2.0 meters, times the cosine of 0 degrees. And in this case, the cosine of 0 degrees is +1. And so if I work that all out, I see that you do 640 joules of work on the bale. Okay? So now I can do this exact same thing, and I can ask, how much work does gravity do while I'm bucking the bale? So in this case, the displacement is still upward, that 2 meters that the bale got lifted during the buck, but the force due to gravity, the weight of the earth on the bale pulling down, is in the opposite direction. And so in this case, theta is 180 degrees. The angle between the direction the force points and the direction that the displacement points is 180 degrees. So I can now solve for the work done by gravity, and that's equal to the force, which we computed was 294 newtons, times the displacement again, which is 2.0 meters, and this time times the cosine of 180 degrees. And what we see there is that the cosine of 180 degrees is -1. That will play an important role here as we go on. And so the work done by gravity in this case is minus 588 joules. So the total work done is the work that you do on the bale plus the work that gravity does on the bale. And so that's equal to 640 joules minus 588 joules, which overall is 52 joules of work was done on the bale during the buck. That's the combined work done between you and the force of gravity. Okay, so I can use that now to figure out the speed, because I know that total work done is equal to change in kinetic energy, and the change in the kinetic energy is a half m. That's not changing in the problem. The final speed squared, so that is the final kinetic energy, minus vi squared, where a half m vi squared is the initial kinetic energy. Well, the bale is getting picked up off the ground, so the initial speed is 0. And what I'm actually interested in is the final speed. So what we get is the total work done on the bale is equal to a half m times the final speed squared. And if I do a little algebra to solve for the final speed, I get Vf squared is equal to 2 times the total work divided by the mass of the bale, or that the final speed of the bale is equal to the square root of twice the total work divided by the mass of the bale. And if I put in my numbers, there's an equal sign there. If I put in my numbers then, this is equal to 2 times 52 joules divided by the mass of the bale, which we said was, what's the mass of the bale? 30 kilograms. All to the 1/2 power, the square root. And if I work that out, I get that this is 1.86 meters per second. So at the moment I let go of the bale, after bucking it up, it's traveling at 1.86 meters per second. Now I could have worked that number out purely from forces and acceleration and using kinematics, but this is an example of how you can solve this problem using energy. Okay, so good luck doing some problems on your own, and we'll do some more problems here again.